This is day 24 of Advent of Code 2024 Done and Go, and this challenge is called Crossed Wires. You and the historians arrived at the edge of a large grove somewhere in the jungle. After the last incident, the elves installed a small device that monitors the fruit. While the historians search the grove, one of them asks if you can take a look at the monitoring device. Apparently, it's been malfunctioning recently. The device seems to be trying to produce a number through some Boolean logic gates. Each gate has 2 inputs and 1 output. The gates all operate on values that are either true or false. So there's an AND gate, produces 1 if both inputs are 1. If either output is 0, these gates output 0. OR gates output 1 if one or both inputs is 1. If both inputs are 0, these produce 0. And XOR gates output 1 if the inputs are different. If the inputs are the same, they output 0. Gates wait until both inputs are received before producing output. Wires can carry 0, 1, or no value at all. There are no loops. Once a gate has determined its output, the output will not change until the whole system is reset. Each wire is connected to at most 1 gate output, but can be connected to many gate inputs. Rather than risk getting shocked while tinkering with the live system, you write down all of the gate connections and initial wire values, the puzzle input, so you can consider them in relative safety. For example, XO and YOO is Z00, X01, XOR, Y01, Z01, and XO2, YO2, Z02. Because gates wait for input, some wires need to start with the value as inputs to the entire system. The first section specifies these values. For example, X001 means that the wire named X00 starts with value 1, as if a gate is already outputting that value out onto that wire. The second section lists all the gates and the wires connected to them. For example, X00 and Y00, Z00 describes an instance of an AND gate which has wires X00 and Y00 connected to its inputs, and which will write its output to YZ00. So in this example, simulating these gates eventually causes 0 to appear on wire Z00, 0 to appear on Z01, and 1 to appear on Z02. Ultimately, the system is trying to produce a number by combining the bits on all wires starting with Z. Z00 is the least significant bit, then Z01, and so on. In this example, the 3 output bits from the binary number 100, which is equal to the decimal number 4. Here's a larger example. After waiting for values on all wires starting with Z, the wires in this system have the following values. Combining the bits from all wires starting with Z produces the binary number that to produce 2024. So simulate the system of gates and wires. What decimal number does it output on the wire starting with Z? Okay, interesting. Okay, well, let's get started. So let's take a look at the input. Okay, so we've got all these X, Y's there. We've got all of these instructions. Does it have every Z1 in there? So Z1, 2. Okay, so it does. When I was just looking at it then I couldn't see that. Okay, so let's get started. So we'll start off with it's got 2 groups of inputs, so we've got that, and then we've got this, so we split on new line. We then we'll do initial values. This can be strings dot split lines 0 and new line, and then we will do what would we call this one? We'll call it gate connections, and that'll be lines 1. So we'll first start off with these, which are the initial values. Actually, these, what are those exactly? What do we call those? Okay, so those are wires. So let's do wire values is equal to make map string int. Is that correct? String int, that is all good. And then let's do gates. This will be for this section, and we will do a map where we take in this string and we get out the inputs and the operator. So make map string, and we'll just make this string 3. List of 3 items. So we will go for line, we'll do for value in range initial values. And what's the, so split on this, so parts equal to strings dot split value, and this, so the wire is parts 0, and then the value will be a string conversion of so dot toy, then parts 1, and then it will be wire values, wire equal value. So I've got that, and now we'll do similar thing for the gates, but we can't do a split on that like we just did. Actually, we could do a split on just this, and that would be so output is equal to parts 1, and then gate parts is strings dot split on parts 0, and that should just be a space. Yeah, so we've split on this, so we've now got this whole part, and now it's just this. So input 1 is equal to gate parts 0, then we've got get input 2, which is the second item, and then we'll have the operator. And now it's gates output is equal to string, and it would be, let's see, input 1, input 2, and then output. No, not output, operator. Okay, so we've got all these gates, and okay, so I know how to do that. So first so we've got the gates, we have then all the input outputs and the operator. So you start off with the gate that we want, so let's say Z01, we then go to the input gates, wires, we look at those and we go to their parents, and then their parents, and so on, until we reach the very top, and then you kind of go your way back down. So we'll do 4 wire in gates. Actually we need, okay, yep, so output bits, this will be, make this a map, so we can have the individual numbers of the Z gates for it. And then down here it would be 4, okay, yep, so because it's binary, so 4, the index would be the bit location in it, so bit value in output bits. So we're using like the number within, we're using the Z number for the output, for the key, but then that's also the location within the base 2 number. So we can just do bitwise map, so method, so let's say output plus equals value, and then we're bit shift bit. Oh, I meant to do range there. Okay, so now for this, if so this is the wire name. Oh, I forgot range here as well. If strings dot has prefix wire then Z, we can then, so we look at the name, it's Z number, and the number is the bit position of the final output, so bit position. This would be equal to basically the string, but everything that's after the Z, and then convert that. So we'd have wire, so 1 and onwards, but then we do string conv dot a toy, and on that, so we've now got the location of a toy. Need to include error the thing there. So now it comes to actually figuring out what the final output is. Okay, so any of there's no Z's in the first one, so no need to look at this. So we're going to input input 1, input 2, operator is equal to gates wire, and then we can do 0. Actually, looking at this should be a function, because everything we're doing for this current wire we're going to have to do for input 1 and 2, and then those inputs and so on. So we'll turn that to a function. Okay, let's just do val, and we'll do calculate wire value. So this will take in a string and return an int, and because it's going to be recursively used, we define it first. And oh yeah, I need to do func like that first. Now we create this, so that is equal to this, and we will do that, but first do wire, and in here we first check if this exists. So if value exists, it's equal to wire values wire, and we can do exists, and let's just return value. So we do that. So with these, we'd be going through all of the inputs. We eventually get to the very top. We then find a value. We then go to the next one. So we're trying to find both the values, input 1, input 2, and then based on that we do the operator. So if we start on the first wire, there is no value here, which is fine. We then go to this. We've got what the input 1, input 2 should be. What we now need to do is figure out what these values are. So it will be input 1 is equal to calculate y value. Input 1, and same for input 2. Actually, I guess that should be not input 1, but the value of it. So we now have both the values. Let's create result. Now we won't initialize it just yet, because we'll be depending on the operator. But this will be return result. So if operator equal to and let's do else if it's equal to or, and else if equal to XOR. So for this, result is equal to val1 and val2. And then for OR, it's equal to val1 or val2. And if it's XOR, XOR. So nice and simple. And so we've got the result of this current wire, which means we should also store it inside of here. So wire is equal to value, no result. So we've done that. So if it already has a value, we return it. We grab the current, we grab the input and the operator for the current gate wire, calculate it. Okay, that seems to be correct. So now back to here, and okay, let's move that down to here. So output bits, and that is bit position, is equal to what I calculate wire value wire. So let's try it on this input and see if we get the correct number. Alright, cool. We got 2024. So let's switch to our input and try it on that. That's a large number, but I guess that makes sense because we're doing bit math on it. So let's enter that in, and that is correct. So let's go on to part 2 now. After inspecting the monitoring device more closely, you determine that the system you're simulating is trying to add 2 binary numbers. Specifically, it is treating the bits on Y starting with X as one binary number, treating the bits on Y starting with Y as a second binary number, and then attempting to add those 2 numbers together. The output of this operation is produced as a binary number on the Y starting with Z. In all 3 cases, Y0 is the least significant bit, then 1 and 2, so on. The initial value for the Y's in your puzzle input represent just one instance of a pair of numbers that sum to the wrong value. Ultimately, any 2 binary numbers provided as input should be handled correctly. That is, for any combination of bits on Y starting with X and Y starting with Y, the sum of the 2 numbers those bits represent should be produced as binary number on the Y starting with Z. So for example, if you have an addition system with 4 XYs, 4 Y, 5 Z, you should be able to supply any 4-bit number on the XYs, any 4-bit number on the Y numbers, and eventually find the sum of those 2 numbers as a 5-bit number on the ZYs. One of the many ways you could provide numbers to such a system should be to pass 11 on XYs, 10011, and 13 1101. If the system were working correctly, then after all gates are finished processing, you should find 24 on the ZYs as the 5-bit binary number. Unfortunately, your actual system needs to add numbers with many more bits and therefore has many more wires. Based on the forensic analysis of scuff marks and scratches on the device, you can tell that there are exactly 4 pairs of gates whose output wires have been swapped. A gate can only be in at most one such pair. No gate's output was swapped multiple times. For example, the system below is supposed to find the bitwise AND of the 6-bit number on 0 through 5. The 6-bit number on 0 through 5 then writes the result as a 6-bit number Z0. However, in this example, 2 pairs of gates have had their output wires swapped, causing the system to produce wrong answers. The first pair of gates with swapped outputs is this and this. Second pair's this and this. Correcting these 2 swapped results in the system that works as intended for any set of initial values on wires. In this example, 2 pairs of gates have outputs that are involved in a swap, but by sorting the output wires names and joining them with commas, the list of wires involved in swaps are these. Of course, your actual system is much more complex than this, and the gates that need their output swapped could be anywhere, not just attached to a wire starting with Z. If you were to determine that you need to swap output wires AAA with EEE over Z99, your output would be there. Your system of gates and wires has 4 pairs of gates which need their output wires swapped. 8 wires in total. Determine which 4 pairs of gates need their outputs swapped so your system correctly performs addition. What do you get if you sort the names of the 8 wires involved in a swap and then join these names with commas? Okay. Interesting. Okay, so with this one, I know I'm not going to be able to figure out the answer in a quick enough time, so thought let's try to ChatGPT it and stuff. So I'm going to start off with actually putting in the answer to see if it's correct, and then we'll go through the code and try learn why it works. Okay, so this code does give the right answer. So let's go to the top here. So I guess similar things. It's getting the lines, wires, operations. It has a mapping of strings to bool for the wrong, which I assume is the wrong wires, or maybe it's the wrong input 1 to input 2. Then for the highest Z. So I've got a process function which is the AND ORs, XORs, that's fine. This is passing the input, which okay, so it's did different to what we did, but yeah, it's just grabbing the input, that's fine. So first it tries to determine the wrong gates. So for op data in operations, actually, so what is operation? So that is the whole thing. Wait, what's op1? Okay, that's a weird variable naming, but it's basically the whole line, so the result is there. So I've got all this. So strings, the result is Z, and op does not equal XOR, and the result is not the highest Z. Wrong result equals true. So something that is worth noting, if you look at all of the Z's in here, most of them are XOR, but there is an AND there. But if you keep going, they're all pretty much XOR. So there's a second OR, there was another OR there. So it's pretty much all XORs, and then there's an AND there. So that's probably the clue for which ones are incorrect. Because I guess like the opposite of OR is AND. So if there are ones which are incorrect, then it's probably swapping the ORs and ANDs. That's my assumption. So if it starts with Z, it's not an XOR, and the res is not the highest Z, is wrong. I'm not sure about why that's part of the condition, but apparently it is. Then we go to the next one. If it is XOR, and it's not a prefix of X and not a prefix of Y, and okay, these are talking about the inputs at the moment. So if input 1 and input 2, if input 1 is not X, although the way it's got these kind of confusing me, but if it's not X and it's not Y, and oh right, the operator is in the middle, that's what's got me. So operator, and then it's this and this. Okay, so if it's not XOR, and the first input's not X, and the first input's not Y, and the second input's not X, second input not Y, and the result does not have a prefix of X, Y, or Z, then wrong is true. If the operator is and neither of them are the first X, it's going through the operations again, looking at the sub operators. If the result is equal to sub 1, or the result is equal to sub 2, and the sub operator is not OR, then it's true. Okay, I'm not 100% following this, but my assumption is there is specific logic within here which after analysing, you would then figure out, and yeah, I don't really have the time to do it, so I thought, hey, let's try figure it out this way, and well, we got the correct answer. So if you like this video, make sure to like and subscribe.